These are the perfect squares up through 20, and then 25 because that one shows up a lot, and then 30, 40, 50, 60, and etc. Because you can see the pattern. 30 squared, well 3 squared is 9, and then you double the zeros. 4 squared is 16, double the zeros. 5 squared, 25, double the zeros. And the same would come if you did like 300 squared. It would be 9, and then you would double the zeros, so I'd have 4 zeros. Okay. This will come in handy for taking roots, because the square root of a perfect square is, well, for example, let's just say the square root of 169. That doesn't work. Well, since 13 squared is 169, the square root of 169 is 13. Questions? So we're going to simplify the following perfect squares. Now, if you have this memorized, it goes really fast. If you don't have them memorized, then you can look at your chart or you can use a calculator. Which of course takes longer than just knowing them. I got that one right, didn't I? Mm-hmm. Yeah. When we have not perfect squares, 200 is not a perfect square. There are two ways to deal with this. We can either know our perfect squares and go, oh, well, 100 is a perfect square, and 200 is 2 times 100. So that's the same thing as the square root of 2 times the square root of 100. And the square root of 100 is 10. So this gives me 10 times the square root of 2. But maybe you don't know all your perfect squares. So the other way to do this is we can make a factor tree. And maybe you get this far and you recognize that 100 is a perfect square and you're done. Maybe you don't. But you're going to make a complete factor tree for 200. And what happens is every matching pair is a little perfect square. So I have 2 2s, that's 2 times 2, that's perfect square. 2 5s is 5 times 5, it's a perfect square. And so what we do is we take one of each of these pairs out. And whatever poor little numbers didn't have matches, those get left behind. They're like remainders. And so what I have is 10 times the square root of 2. And do the same thing with 99. Maybe I recognize that that divides by 9. And 9 is a perfect square. So what I can do is I can take the square root of 9, which is 3, and then leave the 11 behind. Or again, I can factor the 99. I have a matching pair of 3s, so the 3 comes out, and I have a leftover 11, which stays behind. Now if you have more than one number left over, let's say I have an 11 and a 5, then I would multiply whatever numbers are left over, get multiplied back together. And stay inside, and then whatever numbers get pulled out get multiplied together outside. I don't personally recognize any perfect squares inside 324, so I'm just going to factor it. Oh wait, where did I? 16, 2, 8. Oh, there's a perfect square and I didn't even recognize it. Well, that was silly of me. I put a perfect square up here. Okay, well. Let's go to this one instead. Now, when you're doing a factor tree, it doesn't matter how you split the numbers. Like, instead of doing 2 times 720, I could have done 10 times 144 and then split the 10 and split the 144. You know, in various other places, I could have split things different ways. As long as you factor all the way down to primes, you'll get the same factorization no matter how you do it. I like to split with the smallest numbers on the left because then all my primes line up on the one side. That's just my personal preference, but you can don't think that this is the only way to factor this. And then I gather my matching pairs. So I have a 2, and a 3. And then these guys are my left behinds. So I have a 2, a 5, and a 9. Whoops, I don't have a 9. I lied. Sorry, can't circle the 9. And I have to just circle the 5. Right, because 9 became 3 times 3. So I have 2 2s and a 3, so that's 12. And 2 times 5 is 10. So I have 12 times the square root of 10. Okay, well, here's what happened. You can't take the square root of a negative number, right? Because any number squared is positive. Except math kept coming up where you would get a square root that was negative, and mathematicians needed to be able to continue going. Up until that point, you just said, oh, I have the square root of -4, something like that. And then you wrote no solution, and then you were done. But we can't do that all the time. You know, engineering and calculus and higher levels of math where they went, oh my gosh, I have a negative square root, but I had to keep going. So to figure all that out, mathematicians went, I know, we'll make up some numbers. So an imaginary number is just that, is an imaginary number. It is made up. Doesn't exist in the real world. And the way it works is I have the square root of -1 is imaginary. Doesn't exist. It's like mathematician's imaginary friend. Now, pure imaginary numbers are only imaginary. So you have I, or maybe 5 times I, or maybe 6,000 I. But because you're multiplying it by an imaginary number, or by I, the whole thing is imaginary. So this is an I or product. And pure imaginary numbers come when you take a square root of a straight negative. So here's how this works. Square root of 25 is 5, right? The square root of negative, and I'm just going to put a little 1 there, is I. So if I have negative 25, I have a 5 for the 25 and an I for the negative. So the square root of negative 25 is 5I.
So that's what they did.
Yep, they just made it up.
They just started sticking I's in the negative answers.
I's or J's. I because it's imaginary. Yeah. So it's imaginary. They made it up. This is the only part of mathematics that isn't actually like real, but it can still be proven, even though it's made up. Every other thing in math is real. The imaginary numbers are the invention of someone's brain. Yeah, I don't know who, but somebody's brain. So if I take the square root of negative 100, the square root of 100 is 10. So because it's negative 10i. So anytime you have a negative under here, just throw an I on the end. With not perfect negatives that we did with not perfect regular roots, except we're going to add the I to the end. So 27 is 3 times 9, and 9 is 3 times 3. Perfect square. Right here. So I'm going to bring out that 3, and I'm going to bring out the I for the negative, and then this other 3 remains behind. So you have to bring out the I. If I have 216, 2 times 108, which is 2 times 54, which is 2 times 27, which is 3 times 9, and that's 3 times 3. So I have a pair of 2s and a pair of 3s, and a left behind 2 and a left behind 3. So I'm going to have a 2 and a 3 and an I for the negative, and then 1, 2, and 1, 3 get left behind. So I'd have 6I times the square root of 6. Now we can multiply pure imaginary numbers together. So just over here on the side, if the square root of negative 1 is I, then I squared equals negative 1. Okay. Now I to the third is going to be negative 1, because that's I squared, times another I, so it's going to be negative I. I to the fourth, that's the same thing as I squared times I squared, which is negative 1 times negative 1. So that's going to be positive 1. I to the fifth is then positive 1 times another I. So that's going to be I. And then I to the sixth would be I times another I, which would bring me back to I squared, which is negative 1. So it's a rotating pattern. Does that make sense? So basically what I can do is, if I can find a multiple of these, and then I can square it, or, you know, cube it or whatever. So like I to the 6 is equal to I to the 3rd squared. I to the 3rd is negative I. Negative I times negative I is I squared, which is negative 1.
It's just a power.
Yeah. Yeah, it's a repeating pattern, so it repeats. So you can also, if you don't like this method, let's say I want to know what is I to the 7th. If I know I6 is the same as I2, right? So I can go 2, 3, 4, 5, 6, 7. So I to the 7th would be negative I. Or if I want to know I to the 15th, and go 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Again, negative I. So I can just count through the rotation until I get to the number I want. So it's just a rotating pattern. Constant. It's always I's and negative I's and 1's and negative 1's, just repeating over and over and over again. So what we can do then is we can use the fact that I squared is negative 1. Okay. We can multiply the 5 and the 3, and then I have I times I. So basically this is negative 15 I squared, except I squared is negative 1, so this is positive 15. Now do you have to write all that? No. But I just wanted you to see exactly what's happening. So you multiply the number portions, you multiply the imaginary portions, and then figure out what your I is. If it's 2, it's going to be negative 1. If it's 3, it's going to be negative I, etc. And then go from there. Now here, the square root of negative 6 and the square root of negative 15. If I have 2 square roots, I can multiply what's under the square roots together. So I have 6 times 15, which is 3 times 30, which is 90. Let me check myself. Yeah, 90. So it's the square root of 90. 3 times the square root of 10. Because 90 is 9 times 10, and 9 is perfect square, and 3 comes out. Nope, I did that wrong. I lied. Okay, so I lied, so we'll fix it. I forgot you can't. You can, if it was just the square root of 6 times the square root of 15, then I can. But I forgot you cannot do that with negatives. So I have to take the i's out first. So the I times I is going to give me I squared, and the 6 times 15 is going to give me the square root of 90. And I squared is negative 1. So I'm going to have negative 1 times the square root of 90. And 90 is 9 times 10, which 9 is perfect square, so I have negative 3 times the square root of 90. Because I bring the 3 out times the negative 1. So with so if you have a negative in the square root, you have to take out the i's first. And this is what I was talking about. So here's my pattern, right? I squared is negative 1, then I have negative I, and then I have 1, and then I have I, and then it repeats. So if I want to know I to the 23rd, I already know I to the 5th is I. So I can go 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. understanding on that one. So let's do I to the 28. Okay. So again, I'm at 5, so I'm going to go 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28. If you don't want to do all that counting, the other way is, say I take I to the 23rd. This is I. Okay, so this would be I to the 20th times I to the 3rd. And I to the 20th is I squared to the 10th times I to the 3rd. I squared is -1 to an even power, so this is going to be -1 to the 10th I to the 3rd. -1 to an even power is +1, and I to the 3rd is -I. So you can break it that way too. I to the 28th, that's I squared to the 14th. So that's -1 to the 14th, so it's -1 to an even power, so that's +1. So again, you can either count it through the pattern, or you can break it down using powers of properties of exponents. Questions? All right, so we have equations with pure imaginary solutions. I can factor a 4 out of here, but that really doesn't do me a lot of good, because it's not a difference of squares, so it's not factorable with just 2 terms. So what I'm going to do to solve this is I'm going to use the square root property. So I'm going to subtract 256 from both sides, which is going to give me that 4x squared is equal to -256. And then I'll divide both sides by 4. Which is going to give me that x squared is equal to -64. Now, that's what x squared equals, but I want to know what x equals, and so in order to solve that, I need to take the square root of both sides. Square root of 64 is 8, but I have that negative, so it's 8i. Questions? Everybody understand why I did the subtracting 256? Because I couldn't factor? Do the same thing with the next. I'm going to subtract 4 from both sides because, again, I don't have a difference of squares, so I can't factor. It's only 2 terms. I didn't mean to do that in black. So I have x squared is equal to -4. So I'll take the square root of both sides. So I have x is equal to 2i. Now technically, it's not just 2i, and it's not just 8i. Because 8 times 8 is 64, but negative 8 times negative 8 is also 64. So what we want to always do when we take the square root in a quadratic is do the plus or minus in front. So what we have is 8 is plus or minus 8i, or sorry, x is plus or minus 8i, or x is plus or minus 2i. Because that accounts for the fact that you don't know if it was the positive that got squared or if it was the negative that got squared. Okay, so we talked about pure imaginary numbers. And we just worked with some pure imaginary numbers, but then there are things called complex numbers. So what we have is we have real numbers, and we have pure imaginary numbers. And complex numbers occur when real and imaginary numbers get together. It's complex, right? It's complicated. You've got real, you've got imaginary, so it gets all complicated. Make sense? So complex numbers have a real part and an imaginary part. Imaginary has an A in it. Okay. And they are always of the form A plus or minus BI. So they'll either be, take out the plus or minus. They'll either be A plus BI or A minus BI. Where A, that's the real part. And B, or BI, that's the imaginary part. And the reason that you can't put them together is because one part's real, one part's imaginary, so they're not alike. They're not like terms, they don't go together. Yeah, the fabric of the universe would collapse or something, I'm not sure. But real and imaginary together makes complex. All right, so if we're going to add and subtract complex numbers, we can do that. What we do is, first we're going to add the real parts. And then we'll add the imaginary parts. Okay, so I have 5 minus 7i and 2 plus 4i. Well, the real parts are 5 and 2. And 5 plus 2 is 7. And then I have the imaginary parts. And the imaginary parts are negative 7i and positive 4i. Negative 7 plus 4 is negative 3. So 7 minus 3i. So it's kind of the same thing as if you were adding and subtracting with x's and y's and other variables. They act the same way. The only difference is if you square an I, it doesn't just stay I squared, it turns into negative 1. If we're subtracting, first we're going to distribute the negative. Then we'll add the real parts. And then we'll add the imaginary parts. Okay, so if I distribute this negative, what that does is it just changes my signs. So I have 4 minus 8i, and then I have minus 3 plus 6i. Right, because that was positive, this was negative, so all it does is change the sign. So then I have 4 minus 3, so that's 1. Negative 8 plus 6 That's negative 2. So 1 minus 2i. Much the same way we can add complex numbers, we can use those facts to go backwards. And what I have is, I want to know what x and y will make this true. So I need to determine, okay, this is the real portion. This is the real portion. And then this is the imaginary portion, and this is the imaginary portion. So what I have is that 3x minus 5, the real portion has to equal the real portion. So 3x minus 5 equals 7. And then I solve that. So x equals 4. And just like the real portion has to equal the real portion, the imaginary portion has to equal the imaginary portion. So y minus 3i has to equal 6i. Well, I can take the i's away, because what I really need to know is that y minus 3 equals 6. Right? Does that make sense? So I'll add 3 to both sides. So y will equal 9. We'll do another one. Real. Real. Those equal to each other. And I know when you look at it like this and there's letters all over the place, it's very confusing. But when you take that part out and set it as an equation, you've worked these before. So it should look less intimidating. I'm going to have imaginary and imaginary. So I'm going to solve. First, I'm going to subtract 2x from both sides, which is going to give me 3x plus 1 equals negative 2. I'll subtract 1 from both sides, which will give me 3x equals negative 3. Divide both sides by 3. X equals negative 1. Again, on the i's, because the I is on both sides, essentially I just need to know that the coefficients are equal, so I can take the i's away. So I'm just going to do that real quick. And that gives me 3 plus 2y is equal to y minus 6. So I subtract y from both sides. And I get 3 plus y equals negative 6. Subtract 3 from both sides. Y equals negative 9. We're going to use the FOIL method. Okay? And if you recall, that's first, outside, inside, last. So I'm going to multiply first. That's going to give me 2 times 9, that's 18. And then, actually, I'm gonna move that down a little bit so I have more room. Outside. So 2 times negative 3i, that is negative 6i. Inside, 4i times 9, that's 36i. And then last, I have 4 times negative 3, so it's negative 12, and then I times I, which is I squared. Now, I squared is never allowed to stay I squared. So this negative 12I squared is really negative 12 times negative 1. I have like terms, negative 6i plus 36i, so that's going to give me 30i, and I've got that 18. And negative 12 times negative 1 is positive 12.
So do we have to turn that squared I?
You have to, yeah. You have to do
away?
this. So this is going to give me positive 12, right? Because negative times negative. So what this actually is going to equal is 30. Oops, that was in my own way. 30 plus 30i. Okay.
Wait, huh?
You have to take this. Okay. So your negative or your I squared, you can never leave that as I squared. So they gave me the negative 12 times negative 1, so that's plus 12. So this came right there. And then negative 6 plus 36 is where I got the 30i. And then 18 plus 12 gave me 30.
Oh, okay.
And then you changed the 30i.
Hmm?
You changed the 30i.
No, well, negative 6 plus 36 is just 30i. Right, because negative 6 plus 36, the...
Yeah.
Okay. Let's do another one. J. Oh, J. J and I are the same thing. I don't, to be honest with you, I don't really know why they started using J, except for that sometimes they needed to have 2 different letters to mean the same thing in the same problem, I suppose.
Or maybe they just started like doing the i's backwards and on accident, and didn't want it to be a mistake anymore.
So if I squared is negative 1, J squared is also negative 1. Okay. So what we'll do is we'll FOIL. So first, I don't know why that has 2 parentheses, sorry. So 6, outside, so 2 times negative 2, so that's negative 4j, inside. 3 times negative 4 is negative 12j. And then you have last. So I have negative 4 times negative 2 is going to give me 8j squared. Okay. So I'll try to make this less confusing. So first I'm going to combine my like terms on this one. So I've got 6 minus 16j plus 8j squared. But I can't have j squared. So that's 6 minus 16j plus 8 times negative 1. Which I just rewrote. Okay. Well, 8 times negative 1 is negative 8. And then I have these two like terms. So 6 plus negative 8 is negative 2. So that's my final answer. Was that clear at that time? I is not allowed to be in the denominator. The denominator is like a 21 and up club, and I is not 21 yet. It's not allowed to be there. So what you have to do is you cannot have I in the denominator, so you have to do what's called rationalizing the denominator to get rid of I. Now the way to get rid of I is to turn him into a negative 1. So when you have a pure imaginary number, okay, you just multiply the top and the bottom by I. And what I get then when I multiply these, I'm going to get I times 4 plus I, and then I'm going to get 5I squared. So I'm going to distribute this I in the numerator. And I'm going to get 4I, plus I squared. Now I have to square, I'm not allowed to have I, and I squared is negative 1, so that's going to be 5 times negative 1. And I squared, I'm not allowed to have, so that's going to be 4I minus 1 over negative 5. Well, typically speaking, we don't really like negatives in the denominator either. And so to get rid of that, we're going to change all the signs. And finally, our complex numbers, the real part always comes in the front. Okay. So here we changed all signs. And here we move the real part out front. Example, this is complex. And if I just multiply by I, well, this I, on the 6I, that will go away because it'll become a negative 1. But then if I multiply by I, I'm just multiplying 3 by I, and so then I still have another I. So I didn't accomplish anything. So you have to multiply by something called the complex conjugate. Okay? Let's write it up here. Okay, and here's how complex conjugates work. If I have 2 plus I, the complex conjugate is 2 minus I. It's kind of like a difference of squares. And the reason it works is those middle terms, those i's, will go away. If I FOIL these out, if I multiply them together and I FOIL them out, I get 4 plus 2I minus 2I minus I squared. The plus 2I and the minus 2I cancel. So I get 4 plus, because I squared is negative 1, I have negative negative 1, so it's 4 plus 1, so this becomes 5. So complex conjugates get rid of i's. That's their job. So what we have to do is we have to multiply this by its complex conjugate. So if we have a plus here, you multiply it by a minus. If you have a minus, you multiply it by a plus.
Does that mean you multiply all or just bottom?
The whole thing. You have to multiply the top and the bottom by the same, otherwise you've changed the value. So I multiply 3 minus 6i because I had 3 plus 6i. And I'm going to distribute on the top. And that's going to get me 6i minus 12i squared. Right, so 2i times 3 is 6i, 2i times negative 6 is negative 12i squared. And then I'm going to FOIL the bottom. I'm just going to write a little FOIL here, so because I don't have room. And I'm going to get 9 plus 18i minus 18i minus 36i squared. That's ugly. That's also ugly. Okay, whatever. So when I FOIL the bottoms out, this is the whole FOILed part. The 18i's are going to cancel. So those go away. Negative 12i squared becomes positive 12. Because I squared is negative 1, and negative 1 times negative 12 is positive 12. And then I have 9. Negative 36i becomes positive 36. Because I squared again, negative 1 times negative 36, positive 36. I have to put the real part in front. And 36 plus 9 is 45. And just because we like to make things even more complicated, we need to reduce. You can't always reduce. Up here I could not reduce in the first example, but if you look at this bottom, every single thing will divide by 3. You guys see that? So I'm going to divide everything by 3. And that'll be my final answer. Now if you're taking a test and you don't reduce, I'm not going to count the whole thing wrong. I'm going to take off like maybe half a point out of like, if this was a 4-point problem, I'll take off maybe half of a point. Not half of the problem, just half of a point. But you do want to reduce. The square root property is essentially that if I have some perfect, or x squared, y squared, z squared, whatever, and it equals a number, in order to solve that, I'm going to take the square root of both sides. Okay, so x would equal plus or minus 6. So we can use the square root property not just for simple things of this nature, but we can use them. Oh, I lied.
Again?
Yeah, again. I mean, that is part of the square root property, but that's not what I meant to tell you right here. So I didn't lie in that it's not true. I lied in that I didn't give you the right notes. That was true, what I said. It's just not what I meant to say. The square root property is that if I have, let's say I have a plus b squared and that equals 0. That means the square root of a plus b squared equals 0. So that means a plus b equals 0. So we take the square root of both sides. So if I have a square, I mean, I do still take the square root of both sides, except right here I have it equal to 0. X squared minus 25. I can solve this one of two ways. I can either add 25 to both sides, or I can use the difference of squares property. I'm going to add 25 to both sides, because it's perfect. And I'm going to get x squared equals 25. And I'm going to take the square root of both sides. And I'm going to get x is equal to plus or minus 5. Here I have another perfect square. The perfect square trinomial. So x squared plus 6x plus 9 factors perfectly into x plus 3 squared. Right, because the square root of this and the square root of that times 2 gives me the center term. So if I take the square root of both sides, well, the square root of x plus 3 squared is x plus 3. And the square root of 0 is 0. So then I can subtract 3 from both sides. And I get x is equal to negative 3. Technically, it's plus or minus 0, except really you don't have such a thing as negative 0, right? So my answer is negative 3. So I'm going to take the factored form, which is x minus 6 squared, minus because of the negative 12. And that equals to 0. I will take the square root of both sides, and I get x minus 6 equals 0. And I will add 6 to both sides. X equals 6. Right, so perfect square trinomials are going to be of the form a squared. No, that one, hold on. I'm going to use x's. Say a squared plus 2ab plus b squared. Okay, that's a perfect square trinomial. What I'll have is the square root of the first term and the square root of the last term multiplied by 2 makes the middle term. So if I have the way I can tell this is a perfect square trinomial, the square root of x squared is x. The square root of 25 is 5. And if I multiply those two things together and multiply it by 2, I get 10x, which is my middle term. So that lets me know this is a perfect square trinomial. And then the factored form of this is I take my two square roots and whatever sign is right here. So x plus 5 squared. If it was minus 10x, it would be minus 5. Here's what happens. I have a perfect square trinomial, but it's no longer equal to 0. Okay? I just did this. X and 25. So this is going to be x minus 5 squared, but that's still going to be equal to 27. And so I'm going to take the square root of both sides. But 27 is not a perfect square, and that's what makes it irrational. That's why I call them irrational roots. But if I do 27 and I make my factor tree, and I have my pair of threes, so I have 3 times the square root of 3, and again, plus or minus. Because I'm taking out that 3, but it could be negative 3 times negative 3. I don't know. So then I'm going to add 5 to both sides. But I can't really add 5 to 3 times the square root of negative 3, or 3 times the square root of 3. So I'm going to write 5 plus or minus 3 times the square root of 3. And that's going to be my answer. Or, if you want, you can take the calculator out. You can take the square root of 27, which is 5.1961524, whatever. So I'm just going to say 5.2, roughly. So I'm going to have x minus 5 is equal to plus or minus 5.2. And then I'll add 5 to both sides, which gives me that x is equal to 5 plus or minus 5.2. And that means I have to do 5 plus 5.2 and 5 minus 5.2. So that means x equals 10.2 and negative 0.2. So you can either give me an exact answer, leaving the irrational root in, or you can take the square root of 27, round it to the nearest 10th or 100th. I rounded it to the nearest 100th, but that rounded it up, and give me an actual decimal answer.
Can you leave that up, please?
Yeah. Okay, again, perfect square trinomial. And I know that because square root of 16 is 4 times 2 is 8. So this is going to be x plus 4 squared equals 20. And then I'm going to take the square root of both sides. And I'm going to get x plus 4 is equal to 2 times the square root of 5. And the reason I knew that is 20 is 4 times 5, and 4 is 2 times 2. So perfect square. I'll subtract 4 from both sides. Oh, sorry, and that's plus or minus 2. Don't forget that. And so I'm going to get x is equal to negative 4 plus or minus 2 times the square root of 5. Again, if you don't like this, you can take the square root of 20. And you can subtract 4 from both sides. Don't forget though, it's still plus or minus. So I get x is equal to negative 4 plus or minus 4.47. So that means x is equal to negative 4 plus 4.47, so that's 0.47, and negative 4 minus, so that's negative 8.47. These are decimals. Essentially, when we force basically, completing the square is like this. We look at the whatever we're given, and if it's not a perfect square trinomial, we go, no, you will be a perfect square trinomial now. So we're forcing the math to be what we want it to be. And I know that sounds weird, but we are. We're gonna force the math to be what we want to be. And so here's how you do it. If you recall, okay, I'm gonna start without the AX actually. We're gonna start with just the X squared. Okay. What we do, this is the standard form, right? We're going to take B, and we're going to divide it by 2. Okay. But I'm not going to really write it that way. I'm going to write it this way. We take B and we divide it by 2. Okay. So step 1 is B divided by 2. Step 2 is whatever answer we got, we're going to square it. So B divided by 2, whatever number that is, you then square it. And that step 3 is you're going to add both sides. And so what that means is that B over 2 squared equals C. We're going to make B divided by 2 squared to be equal to C. Okay? So on this problem, B is 16. I'm going to divide it by 2. That gives me 8. And I'm going to take that 8, and I'm going to square it, and that's going to give me 64. So C equals 64. So if I'm just finding C, I take B, divide it by 2, and square it, and that gives me C. And then what that means is I would then have a perfect square trinomial, which would then be factorable. So what I did is I created a C that would give me a perfect square trinomial that would make it factorable. Okay, so we're going to take half of 14, well, negative 14. And that's going to be negative 7. And I'm going to take negative 7, and I'm going to square it, which is going to be positive 49, so C is 49. Okay. Questions on that so far?